All right, so let's get started. So one thing is that I didn't give you guys this information, but I asked you to do it on the homework. So I just realized this weekend, and then Nikita came to office hours to ask me about it. And basically, there's a lot of notations to denote what the symmetry properties are. And this is one of the types. So for instance, you already know that symmetry, how it works, right? You have a square. If you have a square, you know that you can rotate it 90 degrees, it come back to itself. You know that you can have two diagonals that is symmetric around those two diagonals, right? So you do the rotation about the axis perpendicular to the square, and that's where you get the 90 degrees. If you have a rectangle, it would be 180 degrees. And then you have those symmetry lines, right? So the basic symmetries of the system can be described with this Schoenflies notation. So for instance, we talked about two-fold rotation. Well, this is defined with C2. So this C2 is a rotation by 180 degrees. And what I told you last time when we were covering symmetry is that it's also called the two-fold rotation. So you see that this C means that is rotation. And what you would do is that you would specify a rotation from around what point on it, right? So similar to that, we would have C3, which is the same thing, rotation but now by 120 degrees. And we call this one three-fold symmetry. Three-fold rotation, sorry. And you have you can continue like that. That's C4. There's C6. In crystals, if you see this, I skip a number, right? Why is that? Does anybody know? So there's the fourfold. There's the sixfold. What happened to fivefold? Does anybody know? I showed you a star, right? And the star has fivefold symmetry. But it turns out that for periodic crystal systems, and the keyword is periodic, there's no fivefold symmetry. Now, people have been playing with shapes, right? Like they make little tiles. And they can get a fivefold symmetry in some systems. So I don't know if you're familiar with Penrose tiles. You guys heard of Penrose? No? All right, I'll show you pictures. I have it in a presentation for next class. So Penrose is the one that got the Nobel Prize. He was famous for gravity along with and collaborated with Stephen Hawking. But he's also a mathematician inclined, and he liked playing with geometric figures. And he came up with something called the Penrose tiles. And those have fivefold symmetry, the tilings that he made. So it turns out that in the 80s, there's a fellow that so one of the things that we do to characterize materials is that we put them under X-rays. And we look at you put a crystal in there, and then we look at the image coming out of the X-ray scattering, which is what we're covering right now, right? And they realized that you can see the pattern, a pattern appear when you're doing the X-ray diffraction on a system, what you put is you put a film around it, and then you can see peaks in the machines that we have upstairs, right, in the lab, that showed you where things show up. But also what people do is that they have like camera film, and they can see where things are scattered from, and they can see the patterns forming in these films. And a crystal that has, let's say, C4 rotation, you would see 4 peaks on the pattern. Or if it had C6 symmetry, you could see 6 or 12 peaks on the system. So it turns out that this guy, back in the 80s, is using a tunneling electron microscope for, this got discovered recently in the 80s, right? He's using it, you focus the beam of electrons in this thing and see how they get transmitted. And he was also getting this scattering pattern from the electrons that had a 5-fold symmetry. But there's no way for something that is crystalline, periodic, to have 5-fold symmetry. So he didn't call those a crystal, he called it a quasi-crystal. So everybody made fun of him when he came out with this discovery. I think he was working at Bell Labs and he got fired. Because how could you embarrass us by trying to publish this? One of the big famous Nobel Prize winners said there's no such thing as quasi-crystals, there's just quasi-scientists. And the guy had to leave his job in the US, he went back to Israel. Turns out he's a Nobel Prize winner because of this discovery. So he found quasi-crystals. And they have the 5-fold symmetry, but it's not something we see in crystals, okay? It's on symmetry that is 5-fold symmetric, but around localized parts. Yeah?
Is this lack of 5-fold symmetry sort of related to a problem of orientational symmetry?
No, it's related to how do you tile a periodic structure with this 5-fold symmetry? And it turns out that you can't, but it's not periodic, it's aperiodic. So think about it like you have 2 crystals coming together, and each of them could have 2 pieces of crystals that could be 5-fold symmetric, and then they come together. You have that edge that they meet together, but the whole thing is not 5-fold symmetric. It's aperiodic because you have different orientations on them. So it turns out that these quasi-crystals are really useful. People didn't know this. And I think if you use a shaver, you have seen that they wear off really fast, right? I don't know if you guys noticed that. Well, not Paul because he doesn't shave. But you only use it for a bit, right? Well, it turns out that if you had a quasi-crystal in the blade, instead of being a perfect crystalline thing, if you had quasi-crystal patterns on it, they last longer. So they started doing that in the blades for your shavers. And they have other uses too. So that's one of the operate. So any number here tells you by how much rotation you will have. We have other operations in it. There's this operation. This is reflection about a plane. So you tell me what plane and how you get reflected. You have another one in that list that I gave you, and this one is inversion. Another one that I gave you in the packet is SN. And what this is that it's going to be a rotation Cn followed by rotation through a plane perpendicular to rotation axis. And I believe that the last one that I give you is E, which is the identity operation. So remember, this is coming from group theory, right? So when we talked about the identity operation on something, it's like in multiplication, if I multiply a number by 1, I get back the same number, right? So that's the identity operation in multiplication. In symmetry operations, the identity operation is that this is the operation that I do to get back the same thing. So that should give you a hint whether something should have the identity operation, yes or no. Does that make sense? So one of the, I believe that some of the ones that I gave you might have a minus sign somewhere here. What does that mean? So what we have is that, for instance, if I have C2, you could have a twofold rotation about the different axes on your molecule, right? And you're going to build this molecule with, I told you, marshmallows and toothpicks, right? And then when you finish, you can eat them. So if you have C2, you can look at your molecule and see that it has twofold rotation and figure out about which axis it has the C2 rotation. You can look at C3 and figure out around what directions in the molecule you're going to have the rotation. So how many operations are you getting for those? And remember that this is the methane molecule that has like, and then one is like behind, right? So it's like this and then one on top. So you can tell that the angle in this direction is 120 degrees, right? In this direction is 120 degrees. In this direction is 120 degrees. And then from this one to this one is also 120 degrees. So the C3, it tells you in what direction, you have to tell it in what direction do I have that symmetry. Make sense? If you have a -1, what we do by notation is that C3 is clockwise and C-3 would be counterclockwise. So clockwise is a positive number, negative number is counterclockwise. And then you have different planes on the system. You can figure out for what planes do I have the symmetry operation. For instance, there's a plane right here, right? Is that symmetric? Yes, no, you figure it out. So you have different planes on your system, right? You can figure out with respect to what planes are those and so forth. Any questions? All right, so if you don't have questions about this notation, then let me go to this, back to this image right here. And this is what we were covering in our previous class, right? There's a nuclei, it's kind of heavy, really heavy, thousands of times heavier than the electron. There's an electromagnetic field, an electromagnetic wave coming, is coming in that direction. Why, maybe? Is this wave moves up and down. The wave vector is ki, and it's going to hit the electron, and it's going to make the electron go up and down, right? Because the wave is an electric field. And then this electron, because it's moving up and down, it can also, is going to become an antenna and is sending waves out. So we can put a detector somewhere and see that how much in this direction R, how much of the wave produced by this guy is being emitted or scattered from the electron. So we have the electromagnetic wave. Let me put this back as review. it has some electric field amplitude. And then is this plane wave. And all of this is in the z-axis, so it's going up and down. So we have two important quantities. One is the wave vector. In this case, this wave vector is related to your wavelength. So for instance, if it's visible light, it's gonna be maybe 300 nanometers in wavelength to 750 nanometers, right? If it's ultraviolet, the wavelength is gonna be less than 200 nanometers. And the other quantity that we have here is omega, which is the angular frequency. So that's the incoming wave. The force experienced by the electron, because the wave is polarized in the z direction, z axis, we're gonna have that there's a driving force. And is the negative, the electromagnetic charge, negative E, the magnitude of this force, and this I omega t in the z direction. So the wave is coming up and down. The electron is going to start going up and down because there's a force driving it in that direction. So this, we're going to assume that it's a periodic function of time. So you can think of that as being a sinusoidal wave, right? This electromagnetic wave is going to be sinusoidal, so it's periodic with time. And this is what is driving the electron. And we're going to assume that the radiation is weak. The electromagnetic radiation is weak. Because it's weak, it produces a small displacement on the electron. If he wasn't weak, then if it's strong enough, it could drive the electron away because he would be strong enough to kick it out of the atom. And after that, we can write Newton's equation. So we would have m, the mass, times the acceleration in the z direction is equal to this force and we also have, I forgot to put it here, the electron is attached to the nuclei through a little spring, right? This is classical physics, so we put springs in there. And this spring has an angular frequency omega naught. And therefore, there's an extra term, omega naught, here. So when omega naught square. So when the electron is moving up, the spring is pulling back on it, right? Trying to bring it back to its position. If it's moved down, the spring pushes it up to the original equilibrium position. Question? So up to here is review. I actually told you what the solution is for this differential equation. So we will have that c as a function of time is equal to some amplitude c naught e to the I, negative I omega t. where C naught has two terms on the bottom, and on the top is the ratio between the electrostatic force, no, sorry, the electrodynamic force, because it's time dependent, on the mass, and then on the bottom is the two frequencies in our problem, the natural frequency of the spring and the angular frequency of the light, radiation, electromagnetic radiation. So that's just your solution. If you're a physicist, you don't have to prove that that's the solution. You can just guess it, and then if you're right, you get full credit. If you're a mathematician, it doesn't work like that. So that's why I'm not a mathematician. So we see that this electron, the motion of the electron, is an oscillations, is oscillatory. The oscillation is related to the incident wave, moving it with a frequency omega. And then this amplitude is related to this ratio. And finally, it means that we have a dipole moment. An electron going up and down, right? It's an oscillating dipole. The dipole moment. And if you haven't seen this in E&M, let me know. It's just this. Questions? I think so. Yeah. So we have that. We have our dipole moment. We know that it's behaving like a dipole moment. And if you go back to E&M, if we have a dipole, you might have seen this in E&M2, right? Maybe you're in E&M2 right now and you're seeing it. If not, you'll see it soon. I don't remember if you see it in physics too. But for sure, in E&M2, you should see this. You have that this oscillating dipole is gonna oscillating dipole radiates an E&M wave. And I know that you've seen it because this is the field of an antenna, a radio antenna. It's just a little dipole on the top. And I know that that's the reason that we probably have to see it, because otherwise electrical engineers would never have seen it before they show up over there. And this scattered electric field at some position R has a time dependence and is related to the incoming wave vector of the wave, some units that have to be there for the 4 pi epsilon naught. Then we have the dipole moment here. This has an angular dependence phi, and this goes in the direction of phi. And then you have that on the bottom is 1 over r. So as this distance r increases, this r gets bigger, the radiation gets smaller. And it's an exponential I k is dotted with r minus the I omega t. All right, so we have this one right here. Let me bring this picture up here. Hopefully we can see the whole screen. All right. So incoming radiation in this direction, that term is there. That's the inverse of the wavelength, the wave vector square. Then we have the magnitude of the dipole moment right here, which is related to these two quantities. We have this angular dependence sine phi. So if you look, you put in your r in some direction, then there's a phi. So for instance, if phi was 90 degrees, then r would be along this x or y axis, sorry. If it's in this angle, maybe 45 degrees, then you know that this changes. And then you have this exponential term which is the same wave gets. The part that is harder to see is what this guy is doing. And what that is doing is that you basically have your little dipole right here, right? So you have that. What's the sign of 90 degrees? 1. So you have that in this plane where phi is 90 degrees is the maximum. What's the sign of 0 degrees? So you have that up here is 0 magnitude. So this scatter wave goes more in this direction than up. So what it ends up looking like is like you have a donut. Does that make sense? There's radiation here, but not up here. So this ends up looking like the electromagnetic field of the donut. All right, any questions? Electron oscillates at the same frequency which way it was driven. The wavelength of this guy, K, the scatter K, would have the wavelength of your system, right? And because they oscillate with the same frequency with which it was driven, then the scatter field has the same wavelength as the incident field. So this Ks can be in a different direction than Ki, but the magnitude would be the same. You didn't change the omega through this interaction. Because your omega didn't change, there's not omega before, omega after, but it's just the same omega. We say that there's no change in energy, and this is an elastic scattering process. So then the sine term gives you the donut shape profile. This is the electromagnetic field coming out of that point. If you have the electromagnetic field, what you're usually looking at is intensity. So you square that up. So now you see that it decays with R squared. So intensity is decaying 1 over R squared. And this is what happens to all of the radiating sources. All right, so this is a complicated equation. And actually I don't think we need all of that. The main thing though is, let me draw this cartoon over here. We have our electron here. This is our electron. This electron, there's a plane wave coming in this direction, and it has some Ki wave vector. And then when it hits this guy, that guy is going to produce waves that go out like that and radiate outward. And this direction, let's say, could be where your K scatter is. if R is pointing in this direction. So this would be, so this is seeing it from the side over here. This one is seeing it from the top. And it's isotropic when you're in the plane of the system. So it wouldn't change. It's just like when you drop a rock in a pond, right? And you see the waves coming out like that out of the rock. That's what you would see from the scattered electron. Questions? So when you when you have a little bob in the lake, you've seen that, right? If you go fishing, exactly like this. So let's see, what do we have? All right, so now let's talk about a scattering cross-section. So let me ask you guys, how familiar are you with the scattering theory? Maybe you have to see it in some classes every now and then, but people sometimes skip it. I know I skipped it in classical mechanics for you too. So you didn't see it with me. You seen scattering? All right. Have you seen a scattering? Yeah. All right. Have you? Have you? Have you? No? All right. Cosmo? All right. Nikita, have you seen scattering before? Sorry? Yeah. All right. So what we're doing now, this is across all of physics, right? Scattering cross sections. What we're doing now is that we have the interaction of matter, in this case, the electron and the nuclei, mostly the electron, interacting with electromagnetic waves. And all of the interaction is basically a little disturbance to our electron that is moving it up and down. So if I come back over here, yeah. So if I look at this one, there's something here, there's something here, and there's something here. Okay? So let me rewrite it as this. Just the magnitude of it, let's not consider but this is just the magnitude of this electromagnetic field. So it's not the vector quantity, but just the magnitude. It basically has a term that goes with the amplitude of the original field. Then a term that I'm gonna call the curly bracket term. And then the other term that is the square bracket over R. Okay, so I'm just using shorthand, but you see it up there what it is, what actually that is. So if we look at it like this, we have that the interaction details are in this curly bracket. So this part right here has all the interaction details. How do we know? Because there's a portion that is related to how strong the electromagnetic field coming in is. There's a portion that tells you that it behaves like a decaying plane wave. But then there's this part here that is important. That is the only one that takes into account what the omega naught was and all of those guys. And that's the interaction details of the system. So interaction details, it's another way to say the interaction details is the cross section of the interaction. So this cross section is the portion of the system that has how strong is the interaction for a particular field that is coming in. So for instance, if you have atoms and I think that this applies to most atoms, maybe all of them, there's a resonant frequency, omega naught, that is related to how the nuclei and the electrons are attached to each other. So in reality, atoms, nuclei are not connected with the spring, right? But this is kind of like a classical version of it. But in reality, there's an interaction between this nuclei and this electron, and that's given to you by some omega naught. And that means that if you drive the system at omega naught, the same frequency of the spring, but in reality, it's not a spring, right? It's the interaction between the electron and nuclei. If you drive it with the right frequency, then something cool should happen, right? That's the natural frequency. And for most atoms, the interaction of the nuclei and the electrons falls in the UV. So for most atoms, omega naught is related to the ultraviolet. Make sense? That's just a quantity, right? So let's look at this equation. For omega of X-rays. So if we're in the X-ray regime, X-rays have more energy than the UV, right? So we're in this regime. Where omega squared is way bigger than omega naught squared. So let me bring this equation over here again. And let me rewrite this term right here. Yeah.
So does that imply that omega is going, or that our driving frequency is going to dominate, is going to be the dominating term in the denominator of our.
Yep. That's exactly what it says. So I had to write this P naught, right? So then this P naught is going to be the term omega squared minus omega naught squared. And then the sign term like this. All right, so you're right. If we're in this limit, we're writing that equation right there. And in this limit, what we're getting is, let me put things in like this. Sorry, this is backwards. Omega squared minus omega naught squared. I switched it because there's this negative in front. So I switched this on the bottom to get rid of the negative. Okay? So now, because I switched it like that, there's omega naught here. But we know that omega naught is way smaller than omega squared. So that means that we're going to get negative ki squared over omega squared. Then I have this E over mass. And then I have the sign phi in the phi direction. All right, So now, what is the relationship between wave vector and angular frequency? Anybody remembers that? No. Mm-hmm. So what that means is that this is equal to -1/4 pi E naught. These two guys cancel out to give you just a mass, sorry, a speed of light. And you get mc squared right here. And then the sign of phi in the phi direction. So if we look at this one, what we have then is that there's no wavelength here. There's no wavelength in this expression. It's just electron charge, electron mass, speed of light, and so forth. So in this limit, there's no mention of the wavelength of the light. So this is actually Thomson scattering. This is one of the experiments that you can do in advanced lab, where the Thomson scattering of a free electron happens. And it's happening because this light that is driving it is actually X-rays. So it's independent of the wavelength. And that's the first term that you would get. Okay? So we know that that's how it happens for X-rays. Now let's look at it in the other limit. Visible light. Yep. In this case, for visible light, then omega squared is going to be smaller than the omega squared naught that is from the UV, right? So in this case, the same term as before, which used to be ki squared 4 pi epsilon naught e squared over m omega naught squared minus omega squared sine phi direction phi. With this simplification, it's now going to become 1/4 pi epsilon naught ki squared over omega naught squared e squared over m sine of phi in the phi direction. And at this point, I can rewrite it and make use of this ki, how it's related to lambda, right? So ki squared gives me pi squared, but pi is on the bottom and on the top, so one of them cancels, epsilon naught. And then I have e squared over m omega naught, and then the sign relation from before, 1 over wavelength squared. So what we see here is that it's inversely proportional to the wavelength, to the square of the wavelength of the incident light. And now we see that in this limit, it is proportional to what light wavelength you're using. All right, so we went through all of this, and what we have here is that whatever this term is, here we were doing, we say that it has all of the interaction details, right? But what we're basically doing is that we have done it for classical electromagnetic waves, and we have two limits. What you would do is figure out what radiation you have, and it works for any type of radiation. It doesn't have to be electromagnetic waves. It could be X-rays, which are electromagnetic waves. It could be UV light. It could be visible light. It could be infrared light. It could also be neutrons. So you can have neutron scattering. And then what you would change is this term in the bracket and put how the quantum mechanical interaction of the incoming nucleon with the nuclei matter. And the outgoing wave would have a term that is really dependent on how the interaction happens. So for some of you, maybe one day you'll get to go to a neutron facility and scatter neutrons of the system. And the neutrons interact really well, not with the electrons, right? But with the nuclei in the system. So X-rays interact with the outer electrons really well. But nuclei and neutrons interact through the strong forces. So they are not sensitive to the electrons because they're neutral particles, the neutrons passing by. So you get more of the nuclei to interact with the neutron. And you also get the same information the X-rays were giving you, but now with the nuclei instead of the cloud of electrons on the outside. So they're really important for coming up with what is the structure of the system that you have. For instance, right now, Dr. Myers is in a beamline, I heard, of X-rays coming into his samples. And he's figuring out what is the structure of the system. So that's what all of this is useful for, figuring out what is the structure of the system. What kind of system do you have? So how does that work? Well, we just figure out how it works for one system right here, right? So what happens if you have more than one system? In that case, you get interference. Let's say we had 2 electrons. My 2 electrons are going to be separated by a distance, let's call it d. Okay, so we have d there. Then we're going to have the radiation coming in this direction. These radiations are plane waves. They're going in that direction with ki being the incident wave vector of that radiation. And when they hit our system here, you're actually going to get radiation coming out like that out of those 2 systems. So the next wave front from the top one and the bottom, they actually come into contact, right? So this wavefronts coming out, you can see that they would come into contact right here. And you get this region right here where the 2 are on top of each other. So at this point, those wavefronts are coming out at exactly the same time, there's going to be a vector in this direction, and this is the scatter radiation going in that direction. So we have a vector that is going like that, and we're really far away, right? That's something maybe I haven't emphasized enough, that our detectors, our atoms are separated at distance d, or electrons here. They're on top of these two electrons are on top of two different atoms. So those two electrons are maybe a distance of a few Armstrongs away. But our detector is going to be, if this is a unit of 1, right? And this is Armstrongs, this distance where our detector is maybe a few centimeters away. So we're saying like millions of times that separation between those two guys, that's where our detector is. So in that case, the wave coming out of this one, even though it looks like a wavefront that is coming out like a circle, right? We're so far away from it that now it looks like a plane wave coming at us. And the wave from this guy is also a plane wave. But now, this one, there's an angle right here. Let's call it 2 theta from this plane all the way up where our detector is. But this wave is not ES, it's actually gains a phase because it's some distance away from our other guy. So it's not traveling, it's gonna be out of phase with the original. Does that make sense? This one is radiating something that looks sinusoidal. This one is radiating something that looks sinusoidal. And then when they get to the same point, there's a difference between the intensity of this one and this one because it's a sinusoidal wave. And that difference is given to you by this phase change. So when the two fields get together, when the two fields get to the detector, they will interfere with each other. And it could be constructively or destructively. So you have those two fields interacting with each other. So when you have constructive interference is when you have this quantity d sine of 2 theta is equal to some integer times the wavelength of the light. You might have seen this in the double slit experiment because this is the same formula in the double slit experiment from modern physics. So here we have a distance, a separation. That distance is the distance between the two slits in the double slit experiment. And then we have an angle here, 2 theta. If you have sine of 2 theta times that distance is equal to a multiple of the wavelength of the light, then you got it. So now, with this, you can see that you would see constructive interference at some particular angle, and that interference is related to the distance between those two atoms. Does that make sense? So now you can tell more or less, because of where I see the interference, now I'm able to tell what is the separation between those two objects. Questions? No? We're good?
Similarly, I suppose for destructive interference, we could measure this by an n+1.
Well, usually nobody looks at destructive interference. You just look where peaks are, right? But yeah, I guess you could look and find some destructive interference. So I'm giving you a very simple explanation of how it works, because I'm saying just one electron in the nuclei, blah, blah, blah. Let's talk about some of the other things that could be happening. Let's say that we have more atoms, more electrons now. So we have one atom, and an atom, unless it's hydrogen, right, has more than one electrons. So if we have several electrons, we have a single atom. It's going to have C electrons. The electrons are in the orbital shells. And we have a very crude way of talking about how, at this point, we're going to use a really crude approximation, right? Like we have them in shells, like the Bohr atom kind of stuff. So that's the atomic model where we have point electrons in orbit around the nuclei. And because the electrons are not in the same place, for the atom, what we will see is interference from these electrons coming in. So when we look at our detector, and it's just a single atom in this case, we're going to look at the scattered electric field coming out, total, and it's going to be some value of this scattered cross-section for each of the electrons. But then we're going to have that each of them has a different phase. And it depends on how many electrons you have, but you could have as many of them phases. So each electron has a different phase from the other ones because they're not in the exact same location as before. Does that make sense? So that would be what you would see for many electron system. All right, any questions at this point? No? So this is the part that I found confusing when I was learning what this was. And let's see, the geometry is really important. So let me see if we can go through this and you guys can see. So the definition of the scattering wave vector. And you guys can see how things are being formed. So we have a phase shift. This is the phase shift, right? Well, we can say that the first one is the phase shift is going to be 0 because we chose that as a reference point. And then there's 1, 2, 3 phase shifts right here because they're a shift from what the first one was. So we can always select things like that. So one thing we could do is actually say that the phase shift so we're going to reference the phase shift from one position in our single atom. What would be a good place to put it in? A place that doesn't move, right? So what doesn't move? The nuclear, right? So we're going to have a phase shift related to that. Let's see. Here is my atom, my nuclei, sorry. There's going to be an electron up here. So that's my electron. And then what we have is that there's incoming radiation, Ki. So there's this guy coming in, there's this guy coming in, and here in the electron, right? So this is a plane wave. So this is my Ki, incoming radiation. From here to here, there's a vector. Let me call this one R1 for electron 1. And then I can make an angle here between those two guys and call this one, what do I want to use, alpha? Let's call this one alpha 1. All right, so at this point, when the wave hits the proton or the nucleus, this wave is going to travel this much distance and then hit the electron, right? So we're going to have a delta R1 distance right there. Questions? No? Make sense? All right. So then this wave gets scattered by this guy, and now let's say it got scattered in this direction. So this is my scattered wave. Goes in that direction. And then there's an angle 2 theta here. So the 2 theta is what we use to describe this angle, because it's actually the position of the detector. The angle of the detector is measured as 2 theta. So we have that 2 theta. And then there's this Ks can be moved in this direction, right? Ks, I can move it here. And we have that guy there.
That also changes the phase.
Yeah, but at this point, I just want to write that guy right there and say that there's an angle right here, which is alpha 2. Okay? All right, so the first thing is that there's this delta R1 right here. And then there's also this distance from from here to here. There's this little distance right here. And then this I'm going to call delta R2. So our phase shift, the path length difference, we can write now the path length difference between those two guys. There's two of them. There's first this part right here. And then there's this little portion right here. And that's our path length difference. So now I can do the geometry for this. And this is the difference between this vector Ki dotted with R1, this portion right here. But this R1 is one vector already. So I don't want to multiply it by a number. I just want the direction of this guy. So then I divide it by the absolute value of that. So that would be my delta R1, the definition of this vector. And then the other vector is the scatter vector. And here we would have Ks dotted with R. Sorry, this is R. Yeah, R1. And then this one is over the magnitude of the scattered wave vector. So now I have both the length of this guy and the length of this guy. And that would mean that would be the path length difference between those two guys when they reach the detector, which is going to be a long, long ways ago in this direction. All right. No, because we have, well, it is a small compared to the big distance to the detector, right? But it is actually encoding the distance between the atoms, in this case, the electrons. Yeah. So this guy is this distance, and we have the vector R1 in this direction. This vector R1 is the one that goes here. Yeah, there's no R2, sorry. Maybe I shouldn't put R1, it should have been just R. Okay, so at this point, we have that we have two vectors. In this case, I have my Ki vector in this direction, and I have my Ks vector in this direction. So what I can do is draw from this point right here. This is my scatter wave vector. It goes like this. So this is Ks. And then I can subtract Ki. So Ki is this vector going in this direction. Here is negative Ki, the incoming radiation. And then we have a vector here. Let me call this new vector Q. And the angle between those two guys is 2 theta. So that's our vectors that we have, the K1, Ki, sorry, Ki, Ks minus Ki give you this Q. So the path length difference is given by that value. And then we have elastic scattering. So that means that Ks and Ki are the same magnitude, right? And what these two guys are is 2 pi over lambda. Questions at this point? So we have the geometry and we have used some of the math so far to look at what is the phase length, the geometry to use the path length difference. Yeah, yeah. So for instance, if you scatter and your electron is going to interact with some other motion in the system, like a phonon, now you grab that phonon and absorb it, and now you have more energy than when the light was coming in. Or you could have that the light comes in, creates a phonon and an outgoing radiation, and the outgoing radiation is less than the incoming one because it created this phonon. So all of those do happen. All right, so because we know this, we can now write the phase difference. And this would be the phase difference between electron 1 with respect to the nuclear, right? Or it could be any of the electrons. not just one. So let me make it for any of the electrons. And this is going to be given by 2 pi times the length, the path travel, the path length difference. This is with respect to the nuclei, right? Over the wavelength. And what we end up getting is that this would be the same as ki vector minus ks dotted with this vector. In this case, it was R1, but here it would be for any of them. So it's going to be Ri. And from this geometry, Qs minus Ks minus Ki gives us Q. And this is a vector. Because we have, this is a really important vector, the vector Q. This is given in this geometric by this red vector right here. And because we have elastic scattering, what we have is that this scattering wave vector is given by 4 pi over lambda sine of theta, where the scattering angle is 2 theta, and this would be half of that 2 theta. All right, questions? So this is complicated. Like I said, I had to draw these things for myself to figure out how they were going. And what we have then is an expression. This would be the electric field generated by all of the electrons, right? And we have the phase factors now here, as you can see. And now, if we want to the electric field from all the electrons, so all of the electrons are generating this scattered electric field, but then it has to get added together, like this expression says here. We would get that this is the total electric field, and it's going to be ES times a summation over however many electrons we have. And here we set a phase e to the I, phi1, phi2, phi3, phi4. But now we know what these phis are, and this becomes e to the negative I q dotted with Ri, the position Ri of each of the electrons. So with that, we see the importance of having this wave vector. By describing this wave vector Q, this wave vector Q right here, this scattering wave vector is help us keep track of all of the phases are. And now we just have that the relative positions of each of the electrons in your system, right? Like you have this Bohr atom that is little point electrons, and they're at different positions. Each of them is contributing differently. And we have the phase difference from the nuclei with that q wave vector. The q is the same for all of them. The Ri is the position of each of the relative positions of each of the electrons from the atom nuclei. Questions? No? All right. So you see what's coming up next. At this point, we figure it out for electrons in one atom. So now what happens when you have a collection of atoms? And now you know that there's a different imposition from each of those atoms, right? The math is going to be the same, and we have something that we can now calculate. All right, so that's my time for today. You guys have a good rest of Tuesday. There's homework due on Thursday. And at this point, I'm not sure how bad the snow might get. For Thursday, what do you guys think? Do you prefer the class online if it's too cold, or do you want to come?
Probably it would be safer for everybody if we did it online.
All right, so we'll do the class online unless the bad weather goes away and it's really nice on Thursday. I'll send a message Wednesday night if we move it to in person. But at this point, I'm thinking that it's probably going to be super cold. And this morning, my truck was frozen. So I don't know. I don't think it's safe to drive when it's freezing. All right. So you guys take care. If you have questions about the homework, remember I have office hours. If you cannot make the office hours, come see me at other times or send me a message. I'll be happy to meet with you. Yeah, I don't